by dx is constant. So by knowing the dt by dx, by knowing the tangent, by drawing the tangent at different points, I can find the heat flux. It is a case where profile is linear, but there will be some other cases like this. Here profile will be non-linear, like this. I will discuss in which cases profile is non-linear. Let's say this is the temperature distribution, and again this is the temperature axis, and this is your x-axis. And suppose you want to find out, again I have chosen 3 points here. First point just at the peak, second point here, and third point, let's say I have taken at the right face. At 3 point, is the flux will be same or different? Please tell me. In this case, as profile is non-linear, so is the flux will be same at all 3 points, or it will be different? Because the Fourier's law can be used to find out the flux by knowing the temperature distribution. Since here, if you draw tangent, you will get the different tangents here. The slope is changing here. If you draw tangent at 3 points, here and here, at all 3 points you have seen the slope is different. At first point, dt by dx equal to 0, because it's a peak. So at this point, what happened? The heat flux is 0. At second point, if you draw tangent, the slope is different. So dt by dx at second point is not equal to dt by dx at third point, and that's why the flux will be different. Yes, very good. So through this way you are able to know that I can find out the flux by knowing the temperature distribution using Fourier's law. This is the first objective, that you must know what is the role of Fourier's law. As in our introduction class, we restricted our attention to simplified condition of one-dimensional steady state in a plane wall. Yes or no? That is a linear profile is there. However, Fourier's law, that if you recall, we have restricted our attention to only a special case of simplest case of one-dimensional steady state conduction in plane wall. But Fourier's law is not restricted only for this. Fourier's law is applicable to unsteady state, multi-dimensional conduction in complex geometry as well. Are you getting a point? So in previous classes, we restricted our attention to simplified condition. What are the condition? It's one-dimensional steady state in a plane wall. Clear? However, Fourier's law is applicable to transient multidimensional Transient means unsteady state, and not for one dimensional only, but also for multi-dimensional. Conduction in complex geometry. Not only in the plane wall geometry, but also in complex geometries we can apply. Clear? Just like here. The objective of this chapter are twofold. First, please write. So, the objective of this chapter is we wish to develop a deeper understanding of Fourier's law. The objective of this chapter is first objective, deeper understanding of Fourier's law. It means what are its origin, what form does it take for different geometries, how does its proportionality constant depends on the physical nature of the medium. इसके अंदर क्या आएगा? Deeper understanding of Fourier's law. It means what are its origin, second, what form does it take for different geometries, how does its proportionality constants depends on the nature of the medium. Means proportionality constant is thermal conductivity, I told you, na? How does the thermal conductivity depends on physical nature of substance or medium. This is the first objective. Our second objective is all 3 points are under the deeper understanding of Fourier's law. Second objective is to develop from basic principles the general equations, college heat equation. To develop general heat conduction equation. Which governs the temperature. See, once I got the heat conduction equation, through this heat conduction equation we are able to find out temperature distribution in the medium in which conduction is the only mode of heat transfer. And solution of this equation will give the knowledge of temperature distribution. And once I know temperature distribution, then I can find out the flux by using which law? So what is the purpose of developing the general heat conduction equation? The purpose of developing the general heat conduction equation is to find out the temperature distribution in a medium in which conduction is the only mode of heat transfer, because we especially deriving the general heat conduction equation, then it means through this equation we are able to find out temperature distribution in a medium in which the heat conduction is taking place. And second, once we got the temperature distribution, then by using the Fourier's law we can find out by using Fourier's law we can find out once I know temperature distribution, that means dt by dx I can calculate. Once I know temperature, by knowing the temperature as a function of x, this is called as temperature distribution. And once I know temperature as a function of x, then by differentiating it with respect to x will give you the gradient. And once I know the gradient, then we can find the heat flux. Yes or no? These are two major objectives of this chapter. Objective is clear, beta? No. So let us start first objective. The conduction rate equation, which is governed by the Fourier's law. Now listen. Now we are going to start the conduction equation from its origin, because I told you what are its origin. Fourier's law is phenomenological equation, that is, it is developed from the observed phenomena. That's why it's called as phenomenological equation. It is not going to derive. For example, let us consider the steady state conduction experiment. A cylindrical rod is there, let's say. A rod is there, try to understand. A cylindrical rod you have. The rod means solid, there is no any hollow portion is there. This cylindrical rod is there. This is of known material. A cylindrical rod is, let's say it's made of iron. And that is insulated on its lateral surfaces. It means all the lateral surfaces are well insulated. What does it mean here? Means no heat transfer is taking place. All the lateral surfaces are well insulated. No heat transfer is possible to the lateral surfaces. Is this clear, beta? Well insulation is there. The insulation is there. Lateral surfaces are insulation. No heat transfer can be taken place. We are talking about heat transfer is only x direction here. This whole length is, let's say, delta x. And its end faces are maintained at different temperature. Let's say this faces, anyhow we have maintained this phase at temperature T1 and this phase as temperature T2. And given that T1 is more than T2, we have maintained the left and right phases at temperature T1 and T2. Clear? Maintain means process is steady state. Means temperature does not going to change with respect to time, although it may change with the location, but at given location it does not change with respect to time. That's called a steady state. And due to this temperature difference, heat transfer is taking place in next direction. Is this clear? So how much variables are there? If you see, we are able to find out the heat flux. Variables are delta T, delta X, area. These three are the main variable: temperature difference, length, and area. Area in direction of heat transfer, these are the variable. If suppose if we keep delta T constant, temperature difference constant, delta X constant. If keeping delta T and delta X constant, varying A, what will happen? A means area normal to direction of heat transfer. What will happen? If we do so, we find heat flux is directly proportional to area. If area becomes twice, then heat transfer will become twice. From this, we can say the heat flux is proportional to area. Heat rate, sorry, not flux. Two dot. Yes, sir. If delta T and delta X is constant, and if we keep varying A, it is found that if area becomes twice, then rate of heat transfer has become twice. Although if delta T and delta X is constant. If keeping delta T and area constant, we observe that and varying delta X, we observe that heat flux heat transfer rate is inversely proportional to delta X. Means less the thickness in direction of heat transfer, more the flux will be there. And finally, holding area and delta X constant, keep varying delta T, it is found that heat transfer rate proportional to temperature difference. So by these three phenomena logical, from these three phenomena, the collective effect I can write as a heat transfer rate is proportional to area into delta T upon delta X. Yes, sir. Please tell me. This is not derivation. It's just a from phenomena, from experiment that we have obtained. This is for a given material. Any problem? what will happen if material has been changed? For example, try to understand. This proportionality constant I will introduce in order to show the effect of material type on the heat flux. Now this material is made of iron. Suppose I change with the steel and rest all as it is. This temperature difference is same, area is same, length is same. Then is the heat flux will be same or different, or heat transfer rate will be same or different? You tell me. If I replace this material from iron to copper or aluminium, then heat transfer rate keeping all other parameter constant. All other parameter means temperature difference we keep same, thickness of the material will remain same, area direction to area and normal to direction of heat transfer is same. So in this case, is the heat transfer rate will be same or different? It will be different. So in order to account the effect of material, effect of medium on the rate of heat transfer, we should introduce a proportionality constant. We have introduced a constant called that K. That K is called thermal conductivity, which accounts the effect of material, which accounts the effect of ability of material to conduct the heat. Clear to you? This proportionality constant may be converted to an equality of introducing a coefficient that is a measure of the material behavior on the rate of heat transfer. Okay, so this Q dot x I can write as a K A into delta T upon delta x. Okay, where K is thermal conductivity. So this is the basic origin, conductivity, clear? And this K accounts which accounts the ability of material to conduct heat. If we are going to evaluate this equation in terms of limit delta x tends to 0, in the limit of delta x tends to 0, if the same equation that I have written here, if I am going to write in the limit of delta x tends to 0, then how I can write this heat rate equation? Then we obtain for the heat rate as Q dot x is equal to minus Ka into dt. Delta become d. dt upon dx is differential change. In how much distance? Del dx. In dx length, the change is dt. Clear? This is the origin of Fourier's law. For heat flux, I can write minus k into dt by dx, because heat flux is the rate of heat transfer per unit area. Any problem, beta? The origin of this derivation, not derivation, origin of this Fourier's law, which is a phenomenological, is clear. Now, the minus sign is here necessary. Now, you should ask the question, sir, why you have put the minus sign here? Because when delta x tends to 0, then delta become d, and delta t upon delta x become dt upon dx, which is called as temperature gradient. But what about minus sign? Minus sign is necessary because heat is always transferred in direction of decreasing temperature. Minus sign accounts the heat always transfer a temperature in direction of increasing x, or you can say temperature decreases with increase in x. That's what is the meaning. Clear to you? And this is the Fourier's law that I have written is only for one dimensional, because temperature is a function of x here only. And one you should always keep in mind, this area in the Fourier's law is always normal to direction of heat transfer. A is the area perpendicular to direction of heat transfer. You can say, what is meaning of this? Direction of, can you say the direction of heat transfer? Direction of heat flow will always be normal to surface of constant temperature called as isothermal surface. Clear है बेटा? Now, at the same time, heat flux is a vector quantity. So since heat flux is a vector quantity, because it must require the direction along with the magnitude. Yes or no? Because suppose I am saying heat transfer rate is 25 kilowatt. So but one question should be, it is incomplete, because we should define the direction. In x direction, in y direction, or z direction. In which direction 25 kilowatt is there. So heat flux is a vector quantity. A heat transfer rate is a vector quantity, you can say. And we can write a more general statement of the conduction equation called Fourier's law as follows. So this is specific for one dimensional. Now more general form of heat conduction equation is here. General form of Fourier's law. Heat conduction rate equation called as Fourier's law. Is as follows. That is what? Q is the heat flux. I'm not going to show direction. This is equal to minus K into gradient of T. This is what the motion. What is the meaning of this? You know, vector quantity means it's Qx into I cap plus Qy into J cap plus Qz into K cap dot dot dot. Clear? This is the meaning of its magnitude and this is direction. This is now here this is heat flux in x direction, heat flux in y direction, heat flux in z direction. And this I can write as a minus K into gradient of T. It means it's a I into, what is the meaning of this? It's a basic mathematics. I into del T upon del x plus J into del T upon del y plus K into del T upon del z. Is this clear? I, J and K are the unit vector in x, y and z direction. And in this case, here temperature is a function of x, y and z and it is a scalar temperature field. Temperature is scalar quantity and gradient of scalar is a vector. Any problem? बोलो बेटा Why I have written the partial derivative here? Because temperature is a function of more than one variable. That's why I should write the partial derivative, partial differential equation. Now, is this clear to you? Yes or no? You can also understand in this way. Let's say this is an isothermal surface is there. Let's say if this surface is an isothermal, okay? It's an isotherm. Because I told you in more general heat, I told you if you recall, the direction of heat flux is normal to cross-sectional area. What direction of heat transfer? It is always normal to area, yes or no? Or more generally, the direction of heat flow, you can also say direction of heat flow will always be normal to a surface of constant temperature. You can say direction of heat flux or heat flow is always normal to area. Also, you can say direction of heat flow will always be normal to surface of constant temperature. It is more general. Why? Why it is more general? Because let's say this is the isotherm here, then in this isothermal surface, if I am talking about the heat transfer, the normal is this. This is the normal here. It's a normal to this surface. Let's say it's n. So this is the normal. It's called as Qn dot. Means heat transfer in normal direction. And always I told you heat flow, direction of heat flux or heat flow rate will be always normal to surface of constant temperature. This is the normal vector to the surface constant surface temperature, and it has two components. It may be three component as well, but I am going to show only two here. It's called as Qx dot, and this is your Qy dot. Yes or no? If I am talking about here x direction and here y direction. So in general, I can write here Q dot as a Qn dot into normal vector. N indicates just like I, J and K na. This indicates you in normal direction. Here in I is the unit vector normal to x, J is the unit vector normal to y. This is the N is also unit vector normal to normal direction of the surface. So you can write here minus k into del t upon del n into n. N is the vector quantity. Is this clear? So, but just it is try to understand, but main equation is this one. So from this, can you say what is Qx dot? If I want to find out Qx dot from this comparison, so Qx dot is nothing, it's minus k into del t upon del x. Qy dot is minus k into del t upon del y, and Qz dot equal to minus k into del t upon del z. Yes or no? And here we have assumed the thermal conductivity will remain same. So we have in this equation we have considered the medium is isotropic. What is the meaning of isotropic? Isotropic medium is the medium for which the value of properties is independent of coordinate direction. Clear? So is the Fourier's law in more general and how it is derived? It is clear. Please tell me. So del T upon del S is the temperature gradient in x direction. This is temperature gradient in y direction. This is temperature gradient in z direction. And listen, in this case, one thing we have assumed the properties, which is called as thermal conductivity of the material, does not going to vary with respect to x. So for an isotropic material, properties does not vary with respect to direction, coordinate axis. You can say also coordinate, sorry, it means direction. So you must ask me what is isotropic material. In this case, the property I am going to bother is thermal conductivity. So as I told you, let's say here I have a slab and I am going to bother about two directions. One is x here and there is y direction here. So in these two directions, the properties here kx y is equal to kz. This thermal conductivity is property, it is not going to vary with the coordinate axis. This is for which material? For isotropic material. Isotropic material. But for anisotropic, property may change, means kx may be not equal to ky, is not equal to kz. This means property of the material may change with direction, with coordinate axis. But it is a very complex cases, and this is not going to shown by all materials. Most of the materials will show the isotropic behavior. Otherwise, for anisotropic material, we should write the Fourier's law as a like this. Q dot vector quantity 2x dot into I cap, 2y dot into j cap, 2 dot z into k cap, where 2x dot will be minus kx into del t upon del x, q dot y is equal to minus ky into del t upon del y, and q dot z equal to minus kz into del t upon del z. It is clear. Kx, ky and kz are the thermal conductivity of the material in three different directions. It is clear. But in the previous, in this we have already assumed material was isotropic. But when it is not isotropic, means anisotropic will be there, then the property will also be changed with respect to direction. Is this clear? So this is what is the more intensive form of Fourier's law, which can be applied for multi-dimensional transient condition and for the complex geometry as well. The only you should keep in mind heat transfer through Fourier's law is taking place in a direction of constant surface temperature, normal to direction of constant surface temperature, or heat transfer is taking place in direction of normal to area. Is this clear? Now we are going to discuss here thermal conductivity in detail, which is the property of matter. Now listen, in order to use the Fourier's law, the thermal conductivity of the material must be known, and this property, which is called as transport property, it depends upon what? Transport property means its ability of material to transport the energy here. And this transport property depends on the atomic and molecular structure of the matter, and therefore it depends upon the state of the matter. Since it depends upon atomic and molecular structure of the matter, and in the case of solid, liquid and gases, atomic and molecular structure of the matter is different, and since this property depends upon the atomic and molecular activity or molecular structure of the matter, that's why it also depends upon the types of fluid or types of substance or types of matter. Is this solid, liquid or gas? Yes or no? So first of all, you must know what is significance of this. It is transport property of substance, matter, and it is a measure of ability of matter to transport the heat. More the K, more easily, more faster, the heat will be transported through that medium. It depends on molecular and atomic structure of matter, atomic and molecular structure matter, and hence It depends on the state of the matter. State of matter. It means is this solid, liquid, or gas? My dear student, as from the Fourier's law, we know very well. Let's say I'm talking about heat flux in x direction is equal to minus k into del T upon del x. From this equation, what is k here? K is nothing. It's a heat flux upon minus of del T upon del x. Same I can write for y and z direction. Similarly, ky equal to 2 dot y upon minus del T upon del y, kz minus 2 dot z upon del T upon del z. For isotropic material, and where kx, ky, and kz are the thermal conductivity of the material in x, y, and z direction. For an isotropic material, thermal conductivity will be independent of direction. Then kx, ky, and kz are same as k. Yes or no? Please tell me. Is this clear? Medicinal for isotropic material. Okay. So how can you define the k? If you suppose if you want to define the k, so as you know from heat flux is equal to minus k in del T upon del x. Yes or no? Then k is equal to qx dot upon del T upon del x. If del T upon del x is equal to 1, then k is equal to qx. So how can you define the k here? Thermal conductivity can be defined as the rate of heat transfer in a given direction where temperature gradient has been maintained to unity in that direction. Yes or no? It's very simple definition. If anyone has asked you to define the thermal conductivity, then it's simple to define the k become q when temperature gradient is unity. So you can define the k thermal conductivity is equal to rate of heat transfer in that direction if we maintain the temperature gradient equal to 1 unity in that direction. Clear? बोलो बेटा. If you want to go again, suppose in simple case I want to define, simple case means one dimensional steady state plane wall. Here is T1, here is T2, here thickness is delta x. Okay. Then in this case q dot we have defined as a minus ka into delta t upon delta x. याद आएगा आपको? In this case, if area is 1, temperature difference is 1, and delta x is 1, everything in 1 meter square, 1 degree Celsius, and 1 meter. in SI system, then Q dot is equal to K, and that will be of unit of watt. So how can define a thermal conductivity equal to, tell me please, can you say here thermal conductivity can be defined as the rate of heat transfer. Thermal conductivity can be defined as the rate of heat transfer if the heat transfer is taking place. Thermal conductivity can be defined as the rate of heat transfer through a material of unit meter thickness across which the temperature difference is unity and area is also unity. Yes or no? The thermal conductivity is a measure of rate of heat transfer. Means, and you can see here, if K is high, the rate of heat transfer is high. If we have maintained the same area and same temperature gradient. In terms of flux, also you can define. If you define the flux, so flux is equal to rate of heat transfer, because flux is what? Rate of heat transfer per unit area. Q dot equal to, simply it's a minus K into delta T upon delta X. So you can define the thermal conductivity is nothing, is the rate of heat transfer through unit area. So actually it is equal to rate of heat transfer. Are you getting it? So thermal conductivity is equal to rate of heat transfer through unit area, because here I equate the K equal to Q dot when area is unity. So that's why we should write here the thermal conductivity is defined as the rate thermal conductivity is equal to rate of heat transfer through a substance across which the temperature difference is unity, thickness is unity, and area normal direction of heat transfer is also unity. Is this clear? Can you define it in this way? So more the K, more the rate of heat transfer if we have maintained the temperature gradient as a unity. For a given temperature gradient, you can say also, for a given temperature gradient, if K is increases, then rate of heat transfer will get, if K become twice, for a given temperature gradient, if K become twice, then rate of heat transfer become twice, because for a given temperature gradient, rate of heat transfer is proportional to thermal conductivity, and thermal conductivity will be equal to rate of heat transfer to a material of unit area, unit thickness, and across which the temperature difference is unity. Is this clear? More the K, more the rate of heat transfer. Clear to you? Clear, beta? यहाँ तक कोई डाउट? Please define thermal conductivity. Anyone? Yeah, yes, it's the ability of material to. I told you, na, Mr. Divyans, I told you कि it is a material. Yeah, more thermal conductivity, more is the heat transfer, because thermal conductivity is the ability of material to conduct the heat, and more the K, more ability, more easily the heat can be transferred through that material under the same conditions. Yeah, if all rest things are same. That's why I told you, na, Q is equal to K. Means more K, more the rate of heat transfer through the material of unit thickness, unit temperature difference, through unit area. Here to you. So K is equal to Q directly, I told you, na. Under which condition? When area is unity, temperature difference is unity, and thickness is unity. So it's directly measure of rate of heat transfer. Now is this clear? Yeah, that is different thing. But A, obviously, if A is more, then rate of heat transfer is more. If all other conditions are same, you should be understand ki what you are keeping the same. Let's say from Fourier's law minus K A into dt by dx. If in the K, if K become twice, twofold, area become half, is there any effect on rate of heat transfer? If thermal conductivity has been increased to twofold and area has been decreased to half, is there any effect on rate of heat transfer? So you should understand ki what if rest to three parameters are there. If then you can say if K become twofold, then Q rate of heat transfer become twice if all other parameters like area and temperature gradient will be constant. It is clear. Then when you can say by increasing the K, we can get the more Q. That's why I fixed here area delta T and delta X as unity, then K equal to Q. Or you can say the Q is directly proportional to thermal conductivity. It means for a given area and for a given temperature gradient, if K become twice, then Q become twice. If K become half, then Q become half. And thermal conductivity is nothing, it's the ability of material to conduct the heat. More K, more easily the heat can be transported through it. Clear? Now at the same time, as far as unity of K is concerned, unit of K is nothing, it's equal to unit of heat flux unit of temperature gradient, yes, no? Or you can say unit of rate upon unit of area in temperature gradient, because as you know, it's nothing, it's a q upon del T upon del x if I'm going to talk about heat transfer in x direction. The unit of heat flux in SI system is what? Watt per meter square. And temperature gradient is nothing, it's degree Celsius per meter or degree Kelvin per meter, both are same. Difference in Celsius and Kelvin is remain same, be careful. Difference in Celsius and Kelvin is same, that's why it doesn't matter. If you solve, this is nothing, it's watt per meter per Kelvin or watt per meter per degree Celsius. Here, they are the unit of K in SI system. Now, come to the, so this is what the thermal conductivity is and how the thermal conductivity will vary with temperature. The effect of temperature on thermal conductivity, I am going to discuss it. हेलो, नमस्कार। अरे कल फोन पे सो गए थे, फिर हम सुबह देखे, मैं कहा सो रहा हो गया, उसने फोन नहीं किया। अरे चलेंगे वही 8:30 तक, 8:30 तक, 8:30 निकलेंगे। सब फोन किए थे, फोन किए थे कि जल्दी से चलना है, हम 8:30 तक निकलेंगे। हाँ, अरे चलिए क्या है, 7 निकलेंगे, एक बना लेंगे। तो एक मार्च से अप्रैल से करना है। हाँ, इन्फॉर्मेशन देखिए आना, मतलब सवाल क्वेश्चन सवाल बनाना होता है, लेकिन जो है इन्फॉर्मेशन लेने में आना चलेगा, लेकिन परसों से सवाल हाँ, अरे इस समय तो 9 बजे पहुँच जा रहे हैं। हाँ हाँ हाँ, तुरंत तुरंत मारते हैं। हाँ, सही बात है। हाँ, हम बताएं, हम बताएं, हमने बताया कि कल तो कोई दिक्कत नहीं है, परसों जा रहा है, लेकिन कल हो गया। और इसको हम बताएं कि मुझे तो बहुत काम है। एक तो जानते हो, कोई भी चीज़ करते हैं ना, सबको मिलता है। अपना भी अपना अलग करो, अपना करो, हमें सबको इन्वॉल्व करना है। तो वही 8:15 8:30 तक निकल लेंगे। हाँ 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 हाँ। वो तो खैर है ही है, लेकिन क्या कर सकते हैं। अरे यार हम आएंगे बताएंगे आपको कहाँ क्या बताएं। No, no, listen. On thermal conductivity, first, because mechanism of heat conduction in solids and fluid are different, so that's why it's a dependency of temperature, dependency of K on temperature will be different in all three medium. So first I'm going to talk about in solids. My dear students, as in the solids, the two main mechanisms is there. In the solid, mechanism is lattice vibration and flow of free electrons. Clear? Now, how the temperature will affect the K? This is the mechanism of heat conduction in solid. Lattice in case of metals, which will dominate? Please tell me. As I told you, in the metals, the flow of electrons are in abundant quantity, and the due to flow of free electrons, the energy is going to transfer from the high temperature to low temperature. Okay. So in metals, which will dominate? Which mechanism will dominate? In metals or conducting solid, you can say. Or in conducting solids, most of the heat transferred through conduction is through flow of free electrons. Yes, most of the heat conduction is through flow of free electrons, and only few is due to lattice vibration. So what happened here? If temperature increases, while in non-metals, while in non-metals, conducting solids, most of the heat transfer is due to lattice vibration. The dominating mechanism is lattice vibration. Okay. So for metals, or conducting solid, what happens? If temperature increases, what happens? If we increase the temperature, try to understand. If we increase the temperature, then obviously molecules on their position will vibrate more violently. Yes or no? And since most of the heat transfer in the metal is due to flow of free electrons, and that flow of free electrons is going to affected due to lattice vibration. Because as temperature increases, molecules vibrate more violently, and this violent vibration of the molecules will hinder the flow of free electrons. Is this clear? And that's why the K will get decreases with increasing temperature for the metals. Clear? The reason is clear. So for the case of metals, as temperature increases, the thermal conductivity will get decreases. You can write in old language. As temperature increases, molecules start vibrate more violently, and that reduces, that restrict the flow of electrons. And since in the metals, the most of the flow of most of the heat conduction is through free electrons, that has been reduced due to excess vibration of lattice molecules, and hence the K will get decreases with increasing temperature. Reason clear? So in this case, as temperature increases, K will get decreases. Means inverse relationship is there for the metals. For non-metals, what happened? Anyone? In non-metals, most of the heat transfer is due to lattice vibration. As temperature increases, then lattice vibration will be more pronounced. Yes or no? And that will obviously add more to the heat transfer. Then here, as temperature increases, K will get increases because because dominating factor in the non-metal or non-conducting solids are lattice vibration. And my dear student, thermal conductivity of the solid is larger than of liquid, and which is larger than of gases. If I going to compare thermal conductivity of solids, liquid and gases, the same substance is there. Just for example, ice, liquid, water and vapor. These three phases are there. In these three states of the matter of the same substance, the thermal conductivity of the ice is more than that of liquid water and is more than that of vapor of liquid. Clear? That should be always remember. The thermal conductivity in the solid is much more than of liquid, and which is much more than that of gases. I will give you one tables. Two table you are able to understand. So what is the reason for K should be decreased with increasing temperature in the metals, and what is the reason for K should be decreased with decreasing temperature, or K to be increased with increasing temperature for the non-metals? Reason is clear. So in the solids, the energy carrier are electrons and phonons. That is vibration also called as phonons. The two main carrier of the energy in the solids. One is phonons, other is electrons. So as a whole, you can say, my dear student, when electrons and phonon means lattice vibration, carry thermal energy leading to conduction heat transfer in a solid, yes or no? Then thermal conductivity may be expressed as, may be written as K is equal to K of E plus K of phonons. Here all that is vibration, you can say Ke means transport of energy due to electrons and phonons. Phonons means that is vibration. and Ke is inversely proportional to resistivity. Where rho E is resistivity. Electrical resistivity, you can say. Electrical resistivity. Rho E is the electrical resistivity. And for pure metals, rho E is low. For pure metals, resistivity is very low. It means if resistivity is low, means K is much higher than kph. So which is dominating here? Most of the heat transfer in pure metals is due to flow of free electrons. For non-metallic solid, where non-metallic solids, K is determined primarily due to phonons. Yes or no? In non-metallic, means non-conducting solids, I am talking about electrical conductivity, not the thermal conductivity. So for non-metallic solids, where flow of free electrons are absent, the thermal conductivity is primarily due to phonons, and this will increases as frequency of interaction between the atoms or lattice. Now, what is the kph? Is the thermal conductivity of the photons. Total thermal conductivity due to lattice vibration, phonons, and this is due to electrons. So now it's clear. In the case of metals, it is mostly due to electrons, and in the metals, resistivity is very low, and that's why, since it is very low, that's why total Ke is much more than kps. This implies the total thermal conductivity is approximately decided by flow of free electrons. Now, in the case of non-metallic solid, where K is equal to K of phonons, because free electrons are absent. Yes or no? Now, thermal conductivity of the phonons will increases with what? As I told you, in non-metallic solids, as temperature increases, then vibration increases, then phonons will increases, then K will increases. In the case of non-metallic solids, in the metallic solids, as temperature increases, the vibration will be affect the flow of electrons, and that's why K will get decreases with increasing temperature. This is clear. Now, in the case of non-metals, these are two types. Listen, non-metals is of two types. It may be crystalline, it may be amorphous. Listen, what is difference in these two? Anyone? One is crystalline, other is amorphous. And in non-metals, we have seen as temperature increases, K increases. But I want to ask you, at a given temperature, which types of non-metal have more thermal conductivity? I'm asking to you. Temperature is fixed here. At a given temperature, which types of metal will have more thermal conductivity? First, tell me what is crystalline and what is amorphous. What is the difference in these two? What is the difference in these two? Yes. The regularity of lattice arrangement has an important effect. Difference in the regularity of lattice arrangements. The regularity, yes, of lattice regularity of lattice arrangement has an important effect on K of phonons. Clear? For crystalline, which is well ordered lattice. For example, material like quartz, any other example of crystalline solids? Quartz, diamond have higher thermal conductivity than amorphous material like glass. Here, so the regularity of lattice arrangement will play a very important role. And how much its importance is there, I want to show you. In a fact, for crystalline non-metallic solids just like diamond or beryllium oxide, kpH, K of phonons can be quite large, exceeding the K of good conductors just like aluminium. Are you getting? At a given temperature, the K of crystalline is obviously more than amorphous, and sometimes the kpH is much more than thermal conductivity of the most of the metals. Is this clear? So crystalline have well ordered lattice, regular lattice arrangement. It have regular lattice arrangement. They are irregular. Now one thing is clear, at a given temperature, the K of crystalline is more than K of amorphous. Both are non-metals. And effect of lattice arrangement is such that sometimes the K of crystalline solids just like a diamond and beryllium oxide have thermal conductivity is more than that of most of the metals as well. Clear to you? So you can write here, in fact, a crystalline non-metallic solid, such as diamond and beryllium oxide its K phonons can be quite large, exceeding the value of K of good conductors such as aluminium. And you should be surprised, at room temperature the thermal conductivity of diamond is highest. Because of which nature? Anyone? The effect of temperature on the solids is clear. In the case of metals or conducting materials, I am talking about electrical conducting materials where electrons are present, the K decreases with increasing temperature, because of flow of electrons is the only mechanism, is dominating mechanism which are going to reduced, hindered by the effect of lattice vibration at a high temperature. That's why K of metals or electrical conducting materials will get decreases with increasing temperature. In the case of non-metals, reverse case is there. But if I am going to compare in the non-metals at the room temperature, the thermal conductivity of the crystalline solid is always more than of amorphous because of regular lattice arrangements. Clear? Because in the crystalline solids, the arrangements is very regular and well ordered, so that phonons can be easily flow and that can contribute more to the heat transfer. Clear to you? So is this clear about the